Okay, so we were asked to compute this line integral of the force function fxy, which is y comma minus x, along the path c, which starts from at the point 1 0 and ends at the point 0 minus 1. In part A, C is the line segment joining these 2 points, and in the part B, it is just the part of the circle joining these 2 points counterclockwise. So C1 is this line segment. It is just the part of the line which is x minus y equals 1, and we wrote the parameterization for this so that when you plug t equals 0, you are at the point 1 comma 0, and when you plug t equals 1, you are at the point 0 comma minus 1, and that's the parameterization. So f dot dr, this is r t, dr is just derivative of this with respect to t, which is minus 1, and then dt. R is y comma x, which is t comma minus 1 minus t minus 1. So you take dot product with minus 1, and you end up with the integral of 1 from 0 to 1, which is just 1. And in part B, so this time we take the parameterization which goes from this point to this point counterclockwise, so like this. Well, this is this part of the circle, so this is 1 comma 0, this is, yok bu böyle değildi. Neydi? Şöyleydi, özür dilerim. 0 comma minus 1, so it is this part of the circle. Okay, now this is the circle x squared plus y squared equals 1. A parameterization for this is just let xt to be cosine t, yt to be sine t, and t starts from 0, and so t is the angle, and it should go up to 3 pi over 2, I guess. Let's check. When you plug t equals 0, you get 1 here and 0 here, so you are at this point. When you plug, for example, so let me just maybe write those down. When you let t equals 0, so xt yt is just cosine 0, which is 1, sine 0, 0. When t equals pi over 2, xt yt is just what? When you plug pi over 2, you get 0, right? Cosine 90 degrees is 0, sine is just 1, so you are at this point, and when you plug pi, you will be at this point, and 3 pi over 2, so xt yt will be just 0 and minus 1, right? Cosine 3 pi over 2 is 0, sine 3 pi over 2 is just minus 1. So this is the correct parameterization. So integral over c, okay, buna c1 demiştik. Buna c2 diyeceğiz. c2 integral over c2 f dot dr is just then t from is from 0 to 3 pi over 2. 3 pi over 2. F was minus y, no, y comma minus x, and then I have dr. Well, rt is cosine t, sine t, so dr is just derivative of these minus sine t cosine t, and then dt. So dr is just minus sine t, cosine t, and then, sorry, dt. Of course, y is just, right, sine t, x is cosine t. So I have this minus sine t, cosine t, dt. Değil mi? X dediğimiz şey cosine, y dediğimiz şey sine. Peki, so the result is then 3 pi over 2. So this is sine squared plus cosine squared. So this is just dt, right? Sine squared t, well, minus dt, maybe. Minus sine squared minus cosine squared. And then, so this is minus t 0 to 3 pi over 2. So we get minus 3 pi over 2. So what we see is then the work done by the force F, from this point to this point along the curve C1 is 1 unit, and along the curve C2 it is minus 3 pi over 2 units. So in this case, the work done along different paths gave us different answers. Remember, in the first example, we had 3 different curves joining these 2 points, right? 1, 1 and 0, 1. The first one was this curve. The second one was this part of this parabola. And the third one was a piecewise smooth curve, line consisting of line segments. And they all gave us the same answer, which was 1. But this time we get different answers. Okay. Now we will see why this is, the case. Peki. All right. We have so-called connected and simply connected, simply connected domains. Okay. Definition. A domain D is called connected if every pair of points, uh, points P and Q in D can be joined by a piecewise smooth curve lying in D. So, for example, something like this is connected, okay? Because whenever I choose a pair of points, let's say P and Q, I can join them by a piecewise smooth curve. This is also connected. Suppose it is this one. Right? Whenever I am given a pair of points, let's say P and Q, I can join these curves, these points via some smooth path. I can join them like this, or like this, right? Several ways of joining these 2 points. But this one is not connected. Which one? Suppose D has 2 parts. Okay. So D is this 2. If you choose the point P from here and Q from this, then you cannot find the path lying in D joining these 2 points, right? There is no path. So this is connected. This is also connected, but this is not connected. Okay. Now, there is another notion. This is the preparation for a theorem we will state about conservative fields. Okay, that's why we are doing this topological work. This is known as topology. So what is simply connected? I said connected and simply connected. Simply connected means there is essentially one way of joining any 2 points. Okay, a simply connected domain D is a connected domain. So it will be connected first, but then there is more than that, in which every simple closed curve, every simple closed curve can be continuously shrunk to a point in D without any part ever passing out of D. Yani şu okay, connected olacak ve her kapalı simple closed curve e, e, kapalı eğri, basit eğri kendisini kesmeyen tek bir noktaya continuously shrunk edilecek. Yani mesela şu. So it is connected and whenever I choose a simple closed curve inside this, suppose this one, okay, I should be able to contract this curve to a point, shrunk this curve to a point continuously. How can I do this? Well, you see, each time I just, okay, choose a parallel copy of this, you know, with smaller curves like this. And continuously I can just shrunk it to a point. Tamam mı? Tek bir noktaya büzebiliyorum. So this is simply connected. But this one this one connected but not simply connected. So here this is just this region. So it has a hole in it, okay? If it is like this, then this is connected but not simply connected. Why is that? You see, take this simple closed curve, okay? Take this simple closed curve. You cannot shrink this curve to a point. Why is that? When you start shrinking this, okay, suppose you do something like this and then like this. Şunu daha ince seçeyim. Suppose first you do this and then you take something smaller, but there is a hole in this, so you cannot just pull this curve to this point or any other point, okay? So this is connected but not simply connected. This definition doesn't reflect why we choose the word simply connected actually to define this concept. Uh, it is hidden in the following. So let me just explain that. Uh, let me write as a remark. Another or şöyle diyeyim, an equivalent formulation of simply connected region is the following. A region or domain, region demeyeyim de domain diyelim, domain dedik. A domain ya da şöyle diyeyim, a connected domain domain D is simply connected if any two paths joining any two given points x and y, p and q, p and q can be continuously deformed to each other, then okay. Bu. Yani ne demek istiyorum? Şunu söylemek istiyoruz. Mesela şu niye simply connected değil? Çünkü şurada iki tane path seçtiğim zaman şu iki noktayı birbirine bağlayan P şu olsun, Q da şu olsun. Bunu birbirine bağlayan bir bu eğri var, bir de bu eğri var. Bu iki eğriyi birbirine dönüştüremem continuous bir şekilde, değil mi? By just pushing one of them, keeping the endpoints fixed, okay? I can come up to here, but I cannot just go over this hole. Therefore, this path cannot be deformed to this path. The lower part of the path cannot be uh, deformed to the upper part. So this uh, region is not simply connected. Okay. Uh, not simply connected. This one is simply connected. Simply connected because whenever I choose 2 points, and any 2 point paths joining these two, one of them can be deformed to the other one, right? I can just deform this path slowly to the other one. Why do we use this word simply? It means the following. The region is connected, so any 2 points can be joined to each other by a continuous path, but it is more than that. There is essentially one way of joining these 2 points. Okay, any two ways can be deformed to each other. Therefore, there is essentially one way. So in this region, there is essentially one way of joining this point to this point, because any two paths can be deformed to each other. Paths that can be deformed to each other are considered the same in topology. So that's why we say that there is essentially a unique path up to homotopy joining these 2 points, because any two paths are equivalent in the sense that one of them can be deformed to other one. But here it is not the case. The point P and Q are joined to each other by several paths, and these paths cannot be deformed to each other. This path cannot be deformed to this path. Okay, that's why it is not simply connected. This is multiply connected. We say that this is multiply connected. Okay, this is multiply connected. Hatta kaç tane olduğunu da söyleyebilirim size. O kazık bir teorem ama şöyle e, şöyle diyeyim. Let D for example R2 minus 0 0. Yani hemen hemen bu resim şöyle. This is not simply, this is multiply connected. D is not simply connected. Indeed, any 2 points can be joined to each other by integer many uh, different paths. Uh, uh, different okay, homotopy classes of paths. Ne kastediyorum? Şunu kastediyorum. Mesela şu iki noktayı birbirine kaç değişik şekilde bağlayabilirsiniz? This can be joined how many ways? This is one way. Okay. Another way is this. You go around this path once and then join this. So this goes around the circle once. Another one goes around the circle twice. So this one. Okay. So this goes around the curve twice. This one goes around the curve once, and this one goes around the curve around the hole just 0 times, right? This goes around the hole 0 times. uh, the yellow one goes around 1 times, blue one goes around it uh, 2 times, this one goes around 3 times. What about I said integer many because I can go the other way around. This one goes around the whole -1 times. It goes the other way around. Okay, so these 2 points can be joined to each other uh, z many times, z many different ways, actually not times but z many different ways. Z here corresponds how many times your curve goes around the origin. It may go around it 0 times, 1 time, 2 time, 3 time, 5 time, or -1 time, -2 times, -3 times. These are all different type of curves. They cannot be deformed to each other. That's a fact which can be proved, but the proof is difficult, so we will not do it. It's a topic in mathematics called homotopy theory or algebraic topology, and this is called actually fundamental group. So we will not go into that, but this is something actually topological. So that's why we call a region simply connected or multiply connected. If any 2 points can be joined to each other essentially in a unique way, meaning that any 2 paths joining these 2 points can be deformed to each other, then we say that that region is simply connected. Uh, and if there are more than one essential ways like this one, then it is not simply connected. Tamam mı? Connected demek iki noktayı birbirine bağlayabiliyorsunuz. Simply connected demek iki noktayı birbirine bağlayan aslında bir tane yol var. Bir tane yol varsa o zaman simply connected diyoruz. Bir sürü yol varsa bunun gibi her bir tam sayı için bir tane yol var. 0 defa dönen, bir defa dönen, 2 defa dönen, 3 defa dönen. O zaman buna multiply connected diyoruz. Bu mesela fizikte işte elektromanyetik teoride falan karşınıza çıkacak bir şey. Niye? İşte bu şeye karşılık geliyor. Hani bu transformatörlerin içinde kaç tur atıyorsunuz? Değil mi? Onun şeyi bu. Yani fiziksel anlamı da var. Okay. Now we have this theorem about uh, conservative fields. It is called independence of path. Okay. Now let D be an open connected domain and let F uh, be a smooth vector field defined on D. Then the following three statements are equivalent are equivalent in the sense that if any one of them is true, then the then so are the other two. Yani ne demek? Ya ikisi birlik, ya hepsi doğru, ya hepsi yanlış. Neymiş bunlar? Şu. F is conservative in D. B, F dot dr over the curve C. Şurada şöyle bir işaret kullanıyoruz. Bu C eğrisinin kapalı olduğunu gösteriyor. Bu integral 0 olacak. Dr is 0 for every simple every piecewise smooth piecewise uh, smooth closed curve in D. And the third one is that given any 2 points, any 2 points, P0 and P1 in D, the integral okay CF dot dr has the same value for all piecewise smooth curves in D starting at P0 and ending at P1. Yani ne diyoruz? D bir tane domain ise o zaman şu üçü birbirine denk. F'in konservatif olması kapalı bir eğri boyunca F'in integralinin hep sıfır olması ve herhangi iki noktayı birbirine bağlayan her eğri boyunca bu integralin hep aynı değeri alması. Independence of path bu yüzden bu teoremin ismi oradan geliyor. So why this theorem is called independence of path? It is because of this part C, meaning that if you have 2 points P1 and P0, then the integral over C1 or C2 or any other curve has the same value, provided that F is conservative. Okay, that's why this is called independence of path. Now let's see why this is true. So A, if you want to show something like this, prove something like this, which states that three conditions are equivalent, then you should be able to prove the following. If A is true, then B should be true. If B is true, then C should be true. If C is true, then F should be true. So let's see how we can prove this. Okay, now A implies B. So we assume that F is conservative, and we would like to prove what? Must prove, must show this integral f dot dr is equal to 0 for every simple closed curve C in D. Okay, now let's see this. Okay, so C is a curve, not necessarily simple, I guess, just a piecewise smooth curve. So it can be something like this. And suppose that RT is a piecewise smooth parametrization for okay, C. Okay, now let me stop. Now I'll continue in the third hour.